Scientists tested a lithium battery that kept 80% capacity after 20,000 cycles. That's the equivalent of driving 8 million kilometers. But there's a catch. You've heard batteries dying after a few 100,000 kilometers. But what if they could last longer than the car itself? In this video, we'll unpack the new single crystal electrode result, how the test was done, why the numbers look so huge, what the real world limits are, and whether this technology actually means cheaper, greener EVs. I'll show the data, explain the engineering trade-offs, and give the one rule you can use today to separate real breakthroughs from the clickbaits. Hello everyone, I'm Shayan, an engineer specialized in electric vehicle development. The headline is simple and irresistible. A research team tested a lithium-ion cell built with a single crystal electrode and cycled it for more than 20,000 charge-discharge cycles, after which it retained about 80% of its capacity. That number gets translated into distance by assuming a typical EV uses about 1 cycle per full charge driving. At 20,000 cycles, that's equivalent to roughly 8 million kilometers. This result comes from work involving Dalhousie University and the Canadian Light Source, and the findings were reported in the Journal of Electrochemical Society. But the lab headline hides the nuance. The cell-level tests use a specific single crystal cathode design that resists the tiny cracks and particle breakup common in traditional multigrain electrodes. When particles crack, they lose electrical contact and the battery ages faster. The single crystal structure dramatically reduces microcracking, which explains the much longer cycle life seen in the lab. Synchrotron imaging showed far less physical damage after thousands of cycles, which is core reason the capacity held up. But translating cell-level success into pack and car-level reality is where the engineering gets messy. A single lab cell cycled under controlled conditions isn't the same as the full battery pack in the car that is charged at different rates, exposed to ambient temperature swings, and pushed with variable power draw. Packs also need thermal systems, mechanical support, high voltage electronics, and cell balancing, all of which influence real lifetime. So while the cell shows the promise of 20,000 cycles, vehicle integration will determine how much of that cycle life is realized in practice. But there is more good news. The researchers used advanced imaging tools to follow degradation in situ. So this isn't a one-off fluke. Looking inside the cell with synchrotron X-rays let the team see where the damage started and how the single crystal electrodes stayed intact. That level of evidence is why multiple outlets and universities are taking this seriously. It's not just a press release, it's a microscopy-backed study published in a reputable journal. But the economics matter too. Single crystal cathodes are more complex to manufacture than some standard powders, and widespread adoption depends on cost, supply chains, and compatibility with existing manufacturing lines. There are early commercial versions of single crystal cathode materials in the market, but scaling to millions of EVs requires investments and process optimization. Some companies and even large OEMs are exploring the technology, but wide adoption will not be instant. But why should drivers care beyond batteries last longer? If battery packs can reach lifetime measured in millions of kilometers, the economics of EV ownership shifts. Battery replacement becomes rare, second life markets using retired packs get reorganized, and the lifecycle carbon math improves because fewer packs need production over the vehicle's life. The researchers explicitly note that ultra-durable cells could outlast other vehicle components and then be repurposed for renewable energy storage. That's a real system benefit beyond the headline. But not every claim is unqualified sunshine. The 20,000 cycle figure depends on how the cycle will run. Depth of discharge, charge rates, temperature, and cutoff voltages all influence aging. In the lab, you can choose conservative cycling protocols to maximize longevity, but real drivers often fast charge, run extremes of climates, and vary driving patterns. So the real question is, can this technology maintain its benefit under real-world usage? Frequent DC fast charging, cold winters, hot summers, and high mileage over many years? That's the next round of testing the community needs. But the implications for sustainability are large if those real-world conditions are met. Batteries that last longer reduce demand for raw materials. cut manufacturing emissions per kilometer, and simplify end-of-life logistics, researchers and environmental analysts point out that if pack only need replacement once every many cars instead of once per vehicle, the net carbon intensity of driving drops markedly. That's not hypothetical. Life cycle analysis show battery manufacturing dominates EV embedded emissions, so longer life helps. But how soon could this show up in your next car? Some single crystal materials are already being produced at scale for certain cells, and there are commercial vendors selling higher durability cathode powders. However, automakers must test pack level behavior, certify safety, and update warranties and service plans. Expect early adoption in premium or performance segments, then wider trickle into mainstream models as manufacturers and suppliers scale up. That pattern mirrors many battery advances historically, first in niche models, then in high volume. But let's be practical. What does 8 million kilometers mean to a driver? If you drive 20,000 kilometers per year, 8 million kilometers equals 400 years, obviously unrealistic per single vehicle. The point is comparative. This battery technology cycles orders of magnitude more than current average cell lifetimes. Typical EV packs today often are warranted for 8 years or 160,000 kilometers in many markets, and many last 200,000 to 400,000 kilometers with decent capacity retention. Moving to an order of magnitude longer cell life changes the replacement calculus and second life viability. The comparison highlights scale, not a literal expectation of centuries of driving. But there are also trade-offs to watch for. Ultra-durable cell chemistries may have different energy densities, cost profiles, or charging characteristics. If a single crystal cathode demands more conservative voltages to maintain longevity, peak range or fast charge speed could be affected. Engineers must balance cycle life, energy density, safety, and cost. The research shows promise on the longevity front, but vehicle makers will evaluate the full performance envelope before committing. But that doesn't mean drivers should wait. The right takeaway is to be excited but realistic. This research shows a real material science path to drastically longer cycle life, supported by robust imaging and multi-year data. It opens the door to batteries that are far less of a lifetime bottleneck for EVs. But the road to mass adoption requires pack-level validation, manufacturing scale-up, and real-world testing under fast charge and varied climates. In short, big potential, believable lab evidence, and a clear list of engineering steps before it lands in millions of cars. Here's the practical rule. Watch how the industry moves from cell-level promise to pack-level performance. If manufacturers can reproduce the single crystal cell's durability in a full pack that holds up under fast charging and heat, this will be a watershed moment. Batteries that no longer limit vehicle lifetimes and that gets repurposed for grid storage. If they can't, the result still buys valuable time. A step change in cell durability informs better pack design and longer second life value, even if the full 8 million kilometer figure doesn't carry through the unchanged. The science is clear, the stakes are high, and the engineers now have a realistic target to chase. To summarize, researchers demonstrated a single crystal electrode cell that lasted more than 20,000 cycles and retained 80% capacity, a lab outcome that maps to the eye-opening 8 million kilometers headline. But the lab cycles isn't equal to the car drives. Real packs have fast charging, temperature swings, and manufacturing scale are the next hurdles. If industry solves those, EVs with batteries that outlast their chassis and slide smoothly into grid roles would be a transformative win for the cost and climate. Until then, be cautiously optimistic, celebrate the material milestone, watch for pack-level validation, and expect early adoption in premium lines before it becomes widespread.